Welcome to EPG Pathshala. The name of this module is minimal sufficiency. The concept of sufficiency and minimal sufficiency has already been introduced in module 6. A minimal sufficient statistic is a sufficient statistic which is a function of every other sufficient statistics. In the present module, we are going to discuss a method for determining a minimal sufficient statistic. First, we shall introduce the concept of partition. Then we shall prove the main result that was due to Lehman and Sheffey in the year 1950. Then we shall prove a property of the minimal sufficient statistics. Some examples are discussed in this connection. Finally, we shall discuss a result for obtaining a minimal sufficient statistic in case of exponential family of distributions. In module 6, we have already introduced the concept of minimal sufficiency. We know that a statistic capital T is called minimal sufficient for an unknown parameter theta if and only if it is sufficient for theta and it is a function of any other sufficient statistic. The factorization theorem given in module 7 enables us to check whether a given statistic, real or vector valued, is sufficient or not. However, it does not provide us any method to obtain the sufficient statistic which will allow maximum possible reduction of data. In the present module, we shall provide a method for determining a minimal sufficient statistic. The following theorem was proved in Lehman and Sheffey in the year 1950. This result is an essential tool to locate a minimal sufficient statistic when it exists. Its proof, however, requires some understanding of the correspondence between a statistic and so-called partitions it induces on the sample space. Let us look at the original data x equals to x1, x2 up to xn, whose realized value is denoted by small x, which is actually a vector value statistic, small x1, x2 up to small xn, belongs to script x. Here script x denotes the whole sample space. Consider a statistic capital T, that is, T is a mapping from script x to some space script T, say. Then for each small t belongs to script T, we define a set script x T equals to set of all x such that x belongs to script x with Tx equals to T, which are disjoint subsets of script x, and also the union of such script x is equals to script x. In other words, the collection of subsets script xt where t belongs to script t forms a partition of the space script x and is usually called a partition of script x induced by the statistic t. It plays a very vital role in determining a minimal sufficient statistic. Now we consider the main theorem. Let us consider the function. The ratio of the joint PMF or PDF h theta x comma y, which is the ratio of product over I from 1 to n f theta xi divided by product over I from 1 to n f theta yi, where f theta denotes the PMF or the PDF and x equals to x1, x2, xn and y equals to y1, y2, yn are any two sample points which are vector valued. Here theta is the unknown parameter Obviously, x and y belongs to script x. Suppose that we have a statistic capital T equals to T1, T2 up to Tk such that the expression hxy does not involve the unknown parameter theta if and only if Tx equals to Ty. That is, Tix equals to Tiy for all I equals to 1, 2 up to k. Then the statistic T is minimal sufficient for the parameter theta. Now we consider the proof of the theorem. We first show that T is a sufficient statistic for theta, and then we verify that T is also minimal. For simplicity, let us assume that f theta x is positive for all x belongs to script x and for all theta. First, we prove the sufficiency part of the theorem. Let us start with script x t such that t belongs to script t, which is a partition of the sample space script x induced by the statistic capital T. In the subset script xt, let us select and fix an element xt, small xt. If we look at an arbitrary element small x belongs to script x, then this element script x belongs to for some unique t, so that both x and xt belong to the same set script xt. In other words, one has tx equals to txt. Thus, by invoking the if part of the statement, we can claim that h theta x comma xt is free from theta. Let us then denote hx equals to h theta x comma xt, which is independent of theta for all x belongs to script x. Hence, we write product over I from 1 to n f theta xi equals to product over I from 1 to n f theta x ti into hx, which can be written as g theta tx into hx, where xt is a vector valued statistic which is xt1, xt2 up to xtn. Then by the factorization theorem, the statistic t is sufficient for the parameter theta. Next, we consider the proof of the necessary part of the theorem. Suppose u equals to ux is another sufficient statistic for theta. Then by the factorization theorem, we can write product over I from 1 to n f theta xi equals to g theta star ux into h star x for some appropriate g theta star and h star. Here h star does not depend upon theta. Now, for any two sample points x, which is x1, x2 up to xn, and y, which is y1, y2 up to yn, from script x such that ux equals to uy, we obtain h theta xy equals to product over I from 1 to n f theta xi divided by product over I from 1 to n f theta yi, which is equals to g theta star ux into h star x divided by g theta star uy into h star y, which is just equals to h star x divided by h star y, because g theta star ux equals to g theta star uy as ux equals to uy. Thus, h theta xy is free from theta. Now, by invoking the only if part, we claim that tx equals to ty. That is, t is a function of u. Now, the proof is complete. To get a clear idea, let us consider some examples. In example 1, Suppose x1, x2 up to xn are IID Bernoulli variables with parameter p, where p is unknown. P belongs to the interval 0, 1. Here, script text is a set containing only 2 points 0 and 1, theta equals to p, and script theta is an open interval 0, 1. Then, for two arbitrary sample points, script x equals to x1, x2, xn and y equals to y1, y2, yn. Both from script x we have product over I from 1 to n f theta xi divided by product over I from 1 to n f theta yi. This is equals to product over I from 1 to n p to the power xi into 1 minus p to the power 1 minus xi divided by product over I from 1 to n p to the power yi into 1 minus p whole to the power a 1 minus yi. This is just equals to 1 by p into 1 minus p whole to the power summation xi minus summation yi. Let us write this as equation 1. From 1, it is clear that the ratio product over f theta product over I from 1 to n f theta xi divided by product over I from 1 to n f theta yi would become free from the unknown parameter p if and only if summation xi equals to summation yi. That is, if and only if summation xi and summation yi are equal. Hence, by the theorem, Tx equals to summation xi is minimal sufficient for p. Next we consider another example. Suppose that x1, x2 up to xn are IID normal mu sigma square variables. Here theta equals to mu comma sigma is a vector valued parameter where both mu and sigma are unknown. Mu belongs to real line and sigma greater than 0. Here script x is the whole real line and script theta is the Cartesian product of r and r plus, where r plus denotes the positive part of the real line. We wish to find a minimal sufficient statistic for theta. Now for two arbitrary data points x equals to x1, x2, xn and y equals to y1, y2, yn, both from script x, we have product over I from 1 to n f theta xi divided by product over I from 1 to n f theta yi. This is equals to product over I from 1 to n 1 by sigma root 2 pi into e to the power minus 1 by 2 sigma square summation over I from 1 to n xi minus mu whole square divided by product over I from 1 to n 1 by sigma root 2 pi into e to the power minus 1 by 2 sigma square summation over I from 1 to n yi minus mu whole square. After some algebraic manipulations, it reduces to the form e to the power mu into summation over I from 1 to n xi minus summation over I from 1 to n yi divided by sigma square into e to the power minus half into summation over I from 1 to n xi square minus summation over I from 1 to n yi square divided by sigma square. Let us write this as equation 2. From 2, it becomes clear that the last expression would not involve the unknown parameter theta equals to mu comma sigma if and only if summation xi equals to summation yi and summation xi square equals to summation yi square. Hence, by the theorem, capital T equals to summation I from 1 to n capital Xi, comma summation I from 1 to n capital Xi square is minimal sufficient for mu comma sigma. Now we move on to third example. Suppose that x1, x2 up to xm are independently distributed normal mu comma sigma 1 square variables, and xm plus 1 up to xn are independently distributed normal mu comma sigma 2 square variables. The two sets of variables are distributed independently of each other. Here the parameter is a vector valued. It is equals to mu comma sigma 1 square comma sigma 2 square. We write it as theta. Here script x equals to r, the real line, and the parameter space script theta is a Cartesian product of r cross r plus cross r plus. We wish to find a minimal sufficient statistic for theta. Now the joint PDF of x1, x2 up to xn is given by f theta x, here x is a vector, this is just 1 by 2 pi to the power n by 2 into sigma 1 to the power n into sigma 2 to the power n minus m into e to the power minus 1 by 2 sigma 1 square into summation I from 1 to m xi minus mu whole square minus summation over I from m plus 1 to n xi minus mu whole square divided by 2 sigma 2 square. Now for two arbitrary data points, one is x, which is x1, x2, xn, and y, y1, y2, yn, both from script x, we have product over I from 1 to n f theta xi divided by product over I from 1 to n f theta yi. This is equals to e to the power minus 1 by 2 sigma 1 square into summation over I from 1 to m yi square minus summation over I from 1 to m xi square minus 2 mu into summation over I from 1 to m yi minus summation over I from 1 to m xi into e to the power minus 1 by 2 sigma 2 square into summation over I from m plus 1 to n yi square minus summation over I from m plus 1 to n xi square minus 2 mu into summation over I from m plus 1 to n yi minus summation over I from m plus 1 to n xi, which is independent of theta if and only if summation I from 1 to m yi square equals to summation over I from 1 to m xi square, comma summation over I from 1 to m yi equals to summation over I from 1 to m xi, comma summation over I from m plus 1 to n yi square equals to summation over I from m plus 1 to n xi square, and summation over I from m plus 1 to n yi equals to summation over I from m plus 1 to n xi. Hence by the theorem, the statistic T summation I from 1 to m xi, comma summation I from m plus 1 to n xi, comma summation I from 1 to m xi square, comma summation I from m plus 1 to n xi square, here T is a vector value statistic, is minimal sufficient for theta, which is equals to mu sigma 1 square and sigma 2 square. Here one can note that theta consists of 3 elements, but the minimal sufficient statistic for theta consists of 4 elements. Next we consider our fourth example. Suppose x1, x2 up to xn are IID uniform 0 theta variables, where theta greater than 0 is unknown. Here the sample space script x is an open interval of real line, it is 0 comma theta, and script theta is r plus, the positive part of the real line. We wish to find a minimal sufficient statistic for theta. for two arbitrary data points x equals to x1, x2, xn and y equals to y1, y2, yn, both from script x, we have product over I from 1 to n f theta xi divided by product over I from 1 to n f theta yi. This is equals to 1 by theta to the power n into the indicator function I 0 less than x ordered n less than theta divided by 1 by theta to the power n into the indicator function I 0 less than y ordered n less than theta. Here I 0 less than x ordered n less than theta takes the value 1 if x ordered n lies between 0 and theta and otherwise. Similarly, I 0 less than yn less than theta is defined. Let us denote a theta equals to the ratio of I 0 less than x ordered n less than theta divided by I 0 less than y ordered n less than theta. Now the question is this: does the term a theta become free from theta if and only if x ordered n equals to y ordered n? If we assume that x ordered n equals to y ordered n, then certainly a theta does not involve theta. It remains to show that when a theta does not involve theta, then we must have x ordered n equals to y ordered n. Let us assume that x ordered n not equals to y ordered n. Then we have to show that a theta must depend on the value of theta. Now, for the sake of simplicity, suppose that x ordered n equals to 2 and y ordered n equals to 0.5. Then a theta equals to 0 when theta equals to 1, a theta equals to 1 when theta equals to 3 and a theta equals to 0 by 0 when theta equals to 0.1 respectively. Clearly, a theta will depend upon the value of theta whenever x ordered n not equals to y ordered n. We assert that the term a theta becomes free from theta if and only if x ordered n equals to y ordered n. Hence, by the theorem we claim that capital T equals to x ordered n, which is the largest order statistic, is minimal sufficient for theta. Now we consider a very important result. Result 1. Any statistic which is a one-to-one function of a minimal sufficient statistic is itself minimal sufficient. Let us consider a proof of this result. Suppose that a statistic S is minimal sufficient for theta. Let us consider another statistic capital T equals to Hs, where H is an one-to-one function. We know that one-to-one function of a sufficient statistic or a jointly sufficient statistic is also sufficient or jointly sufficient, and hence T is sufficient for theta. Let U be any other sufficient statistic for theta. Since S is minimal sufficient, we must have S equals to g of U for some function g, because S is a function of every other sufficient statistics. Then we obviously have T equals to Hs, which is equals to h of gu, and therefore T is also a function of U, which verifies that T is minimal sufficient. Let us consider an example. Suppose x1, x2 up to xn are IID normal random variables with parameters mu and sigma square. Here theta equals to mu comma sigma, and both mu and sigma are unknown. Mu belongs to real line, sigma greater than 0. Now we know that the statistic T, which is equals to summation xi comma summation xi square, is minimal sufficient for mu comma sigma. Now x bar, which is actually 1 by n summation xi, and s square, which is 1 by n minus 1 summation xi minus x bar square, being a one-to-one function of t, so we can claim that x bar s square is also minimal sufficient. Now let us close our discussion with the following result, which provides an useful tool for finding a minimal sufficient statistic within a k parameter exponential family of distributions. It is a hard result to prove. One may refer Lehman and Casella, the book of Lehman and Casella in the year 1998 for some of the details. Now the result is, suppose that x1, x2 up to xn are IID with common PMF or PDF belonging to the k parameter exponential family that we have already discussed in our module 8. PDF or PMF f theta x equals to u theta into Vx into e to the power summation I from 1 to k q I theta into t I x with some appropriate forms Vx greater than equals to 0, u theta greater than equals to 0, q I theta and t I x I from 1 to k. Now if we define the statistic capital Sj, which is summation over I from 1 to n tj xi, j from 1 to k, then it can be shown that the statistic S, which is a vector value statistic which consists of S1, S2 up to Sk, is jointly minimal sufficient for the parameter theta, which is also vector valued with k components. In the present module, we have seen that how one can derive a minimal sufficient statistic by using the theorem provided by Lehman and Sheffey, such as one can obtain a sufficient statistic by using the factorization theorem. We have seen that the concept of partitioning of sample space plays a very vital role in proving the theorem. We have derived a very important property of the minimal sufficient statistic, which states that if t is minimal sufficient, then any one-to-one function of t is also minimal sufficient. We have noticed an interesting fact that when t is a vector valued minimal sufficient statistic, then it may have more elements than the parameter theta, which is also vector valued.